Jai Hind everyone. This lecture is of the subject Energy Science and Engineering, subject code KOE 033. In this particular lecture of the subject, I am going to take one topic of second unit that is based upon the nuclear energy, and the topic which I am taking here is nuclear reaction and the nuclear reactor. So starting with what are the nuclear reactions? Nuclear reactions are the reactions involving the participation of atomic nuclei. Some of these reactions are spontaneous, as for example the radioactivity, while few others are result of bombardment of nuclei with an energetic particle or radiation. There are certain similarities and differences between nuclear and the chemical reactions. The similarity lies in the fact that both these type of reactions actually obey the conservation laws, conservation of mass, conservation of energy, particles and the charge. The difference lies in the amount of energy released. They are similar, nuclear reactions and the chemical reactions are similar, but let us see what is the difference. The major difference lies in the amount of energy released. Nuclear reactions are highly energetic as compared to the chemical reactions. For example, the fission of an atom of uranium-235 releases about 210 MeV of energy, while the energy released due to the formation of one molecule of CO2 from combustion of carbon is about 4.08 eV only. So we see that they are similar, but the major difference is in the amount of energy released by them. The type of nuclear reactions which are of importance in the nuclear reactors are the elastic scattering, the inelastic scattering, the neutron capture and the fission. All these nuclear reactions are of importance in the operation of nuclear reactors. So let us see what is the elastic scattering. This is a type of neutron reaction or nuclear reaction involving the elastic collision of a neutron with the nucleus, right? So elastic scattering is nothing but a type of nuclear reaction which involves the elastic collision of a neutron with a nucleus. The structure or mass of nucleus does not change as a result of this reaction. So elastic scattering is not going to change the structure or the mass of the nucleus, right? However, the speed of neutron and its direction changes. As a result of the elastic scattering, the speed of the neutron involved in the elastic scattering process changes and the direction as well. As the name suggests, elastic scattering suggests that there is no change in the kinetic energy of the system during this event, though the neutron loses a part of its kinetic energy and slows down. Now let us see what is the utilization of elastic scattering in nuclear reactors. The elastic scattering is utilized in nuclear reactors is the scattering of neutron by reaction with light nuclei, right? The elastic scattering utilized in the nuclear reactor is the scattering of neutron by reaction with light nuclei, for example, hydrogen, deuterium, carbon. This results in loss of kinetic energy of the neutron. Actually, a large loss of kinetic energy of the neutron, but without any loss in the number of neutrons. This process is actually called the moderation, and the substances containing light nuclei are called the moderator. So, moderation in moderation in nuclear reactors involve the elastic scattering. Then comes the inelastic scattering. This is a type of neutron or nuclear reaction involving inelastic collision of a neutron with the nucleus. The nucleus reaches an excited state upon neutron irradiation. This is what happens in inelastic scattering. Now, the nucleus reaches an excited state upon neutron irradiation and decays rapidly to the ground state. This is accompanied by emission of the gamma radiation. So, here you can see that a neutron with inelastic collision, having inelastic collision with U-238, because of this U-238 enters in the excited state and later on this results in gamma radiation during the process. For inelastic scattering to occur, the energy of neutron incident on a nucleus must necessarily be greater than the excitation energy of lowest state of the nucleus, right? This initial slowing down of neutron in a reactor system is due to inelastic collision, inelastic scattering. The initial slowing down of neutron in the nuclear reactor is due to the inelastic scattering. Then comes the other nuclear reaction, which is said to be the neutron capture. Different form of elastic and inelastic scattering where there is no change in the atomic mass of target nucleus. Neutron capture is actually different from the elastic and inelastic scattering in a way that it results in increment in the mass of target nucleus which reaches the excited state, right? So, in elastic as well as inelastic scattering, there was no change in the atomic mass of the target nucleus. But in neutron capture nuclear reaction, there is a change in the mass of the target nucleus, and this change is also accompanied by this is also accompanied by a change in the state of the nucleus, right? For this, let us consider the following example. A neutron is captured by uranium-238. The uranium-238 changes to uranium-239 and U-239 is actually in the excited state. The excited nucleus then decays rapidly within 10 to 13 seconds by emission of the gamma radiation. So, the entire process of neutron capture is this. A neutron captured by uranium-238 which gets converted to uranium-239, but upon capturing a neutron, the uranium-238 which is getting converted to uranium-239 is actually in the excited state. This excited state decays rapidly. This is the duration in which the excited state decays, and we can very well see by this reaction that the process is accompanied by gamma radiation. The importance of neutron capture in a nuclear reactor is as follows. Neutrons are captured by control rods which otherwise might initiate the fission. When cadmium is used as control rod, when boron is used as control rod. The reaction is shown over here. This is the reaction of the neutron capture. Now, transformation of one nucleus to the other is due to neutron capture enabling production of isotopes of interest. For example, radioactive cobalt for medicinal uses involve the process of neutron capture. Radioactivity. Early experiments revealed three types of nuclear rays or the radiations. These three types of nuclear rays or nuclear radiations were alpha rays, beta rays and the gamma rays. These three types of radiations are differentiated by their ability to penetrate matter. Alpha radiation is barely able to pass through a thin sheet of paper, whereas beta radiation can penetrate aluminium to a depth of about 3 mm, and as far as the gamma radiations are concerned, they can penetrate lead to a depth of 2 or more centimeters. A comparison of penetration depths of alpha, beta and gamma radiations through various materials is shown over here. You can very well see the alpha radiation, the beta radiation and gamma radiation penetration through various materials. So, what we can see over here is alpha radiation cannot penetrate the paper, right? Alpha radiation is barely able to pass through a thin sheet of paper, and same thing is shown over here. This is the sheet of paper and the alpha radiation is not able to pass through this paper sheet. Then comes the beta radiation. We can very well see from here that beta radiation can pass through the paper, they can penetrate the metal, they can penetrate aluminium to a depth of about 3 mm. It is shown over here that they are able to penetrate, but they are not able to pass through the metal if the depth is more than 3 mm, right? Gamma radiations can penetrate lead to a depth of 2 or more centimeter. Gamma radiations can penetrate the paper, they can pass through the paper, they can pass through the metal, they can pass through the concrete and they can penetrate lead up to a depth of 2 centimeter, 2 or more centimeters, right? Now, let us see the electrical properties of these three types of radiations. The electrical properties of these three types of radiations are actually investigated by passing them through a uniform magnetic field. This is shown in the figure here, right? So, for investigating the electrical properties of these rays are passed through a magnetic field. According to the magnetic force equation, F equals to QVB, positively charged particles are deflected in upward direction, negatively charged particles are deflected in downward direction, and the particles with no charge pass through the magnetic field undeflected, right? So, positive charges, positively charged particles are getting deflected upward, negatively charged particles are getting deflected in downward direction, and the charges without any and the particles without any charges will remain undeflected, right? So, eventually alpha rays were identified with helium nuclei rays with electrons and positrons, and gamma rays with high energy photons. We discuss the alpha, beta and gamma radiation in a bit detail. The effect of magnetic field on alpha, beta and gamma radiation can very well be seen from the schematic representation here. The relative paths of the particles depend upon their masses and the initial kinetic energy. So, alpha particles being positively charged are getting deflected in upward direction, beta particles being negatively charged getting deflected in downward direction, and gamma particles which are not at all charged remains undeflected here. Now let us see what is the alpha decay. Heavy unstable nuclei emit alpha radiation. In alpha particle decay, or simply the alpha decay, the nucleus loses 2 protons and the 2 neutrons. So the atomic number decreases by 2, whereas the mass number decreases by 4, right? Before the decay, the nucleus is called the parent nucleus. The nucleus or the nuclei produced in the decay are referred to as the daughter nucleus or the daughter nuclei. Let us see the representation as given over here. Here, ZXA is parent nuclei, Z2A4X is daughter nucleus, Z-2, A-4 is daughter nucleus, and 2He4 is alpha particle. An example of alpha decay is the decay of uranium-238, which is shown over here. Decay of uranium-238. The decay of uranium-238 into thorium-234 and helium. Beta decay. Nuclear beta decay involves the conversion of one nuclei into another. For example, a neutron can decay to a proton by emission of an electron, and a nearly massless particle called an anti-neutrino V, represented by V, right? So, nuclear beta decay actually involves the conversion of one nuclei into the another one. For example, neutron decay to a proton. This is shown over here. The notation -1 E0 is used to designate the electron. Its mass number is 0 because it is not a nucleon, and its atomic number is -1, and this signifies that it is carrying a charge of E, right? The proton is represented by 1p1 because its mass number and atomic number are both 1. When this occurs within an atomic nucleus, we have the following equation for the beta decay. The reverse process is also possible. A proton can decay to a neutron by the emission of a positron, which is positively charged beta particle, and a nearly massless particle called neutrino, denoted by V. This reaction is denoted by the following equation. Right. The positron 1e0 is emitted with the neutrino V, and the neutron remains in the nucleus. It is represented by the equation over here. Let us see the gamma decay. A nucleus in an excited state can decay to a lower level state by the emission of a gamma ray photon. This is known as the gamma decay. This is analogous to de-excitation of an atomic electron actually. The gamma decay is represented symbolically by the equation given over here. The asterisk over the nucleus actually indicates that it is in excited state. In gamma decay, neither the atomic number or mass number changes. So, there is no change in the atomic number and the mass number, and hence type of nucleus does not change. Now let us come to the operation which takes place inside the reactor. It is the nuclear fission. So, fission process in the reactor. When nucleus of an atom splits into lighter nuclei through the nuclear reaction, the process is termed as nuclear fission. We know that. This decay can be a natural spontaneous splitting by the radioactive decay, or it can actually be simulated in a lab by achieving the necessary condition, that is bombarding with the neutrons. right? Bombarding the fissionable atoms by the neutrons. The resulting fragments tend to have a combined mass which is actually less than the original mass. The missing mass is what is converted to the nuclear energy. It is the mass defect that gets converted into nuclear energy in the mentioned nuclear reaction. Therefore, the nuclear fission is defined as the process in nuclear physics in which nucleus of an atom splits into two daughter nuclei, right? Let us see the example of nuclear fission. An example of nuclear fission is the splitting of uranium-235. The equation of reaction can very well be written over here. It is fission of uranium-235 by bombardment of one neutron, and you can see the daughter nuclei so formed, the barium and the krypton, and in this process 3 neutrons are also released, and the process releases an energy equivalent to 210 MeV. The splitting of nucleus is called the fission. Now, it is very interesting to know that uranium-235 fission does not always produce the same fragments. Certain other examples of uranium-235 fission are shown over here. One which we have already shown. Q is showing the energy released in the process. The fission of the uranium-235, the daughter nuclei produced are Ba and Kr. It may result in daughter nuclei as Xe and Sr. It may result in daughter nuclei as Sn and Mo. 3 neutrons are produced here as well, and certain amount of energy is released. A high amount of energy is actually released. Now, in each case, the sum of the masses of product nuclei are less than the masses of the reactants. So, the fission of uranium is an exothermic process where Q is more than 0, right? Energy is released by the process. So, it is an exothermic process. This is the idea behind the use of fission reactors as source of energy. As the process is exothermic, that's why it can be employed as the source of energy. The energy carried away by the reaction takes the form of particles with kinetic energy. The other example of nuclear fission is splitting of uranium-233. The equation of the reaction is given below. Uranium-233, bombardment of a neutron results in, this is the parent nucleus, and it results in the daughter nuclei as Xe and Sr, and the process releases 3 neutrons. Also, the plutonium-239 is another example of nuclear fission, and it is given by the following equation. Plutonium, the parent nuclei, the daughter nuclei are Xe and Zr, and again 3 neutrons are produced in the 3 neutrons are released by this fission reaction. Now, let us consider the chain reaction. What is the chain reaction? A chain reaction is that process in which the number of neutrons keep on multiplying rapidly during fission till whole of the fissionable material is disintegrated, right? The chain reaction will become self-sustaining and self-propagating only if for every neutron absorbed, at least one fission neutron becomes available for causing fission of another nucleus, right? This condition can be conveniently expressed in the form of multiplication factor or the reproduction factor of the system. It can be expressed as K equals to number of neutron in any particular generation divided by number of neutron in any preceding generation. Now, if K is more than 0, chain reaction will continue, right? If K is less than 0, chain reaction cannot be maintained, and if K is equal to 1, the critical chain reaction results in constant power output by the reactor. Uranium-235 fission can produce a chain reaction. In a compound consisting of many uranium-235 nuclei, neutrons in the decay of one U-235 nucleus can initiate the fission of additional uranium-235 nuclei. This chain reaction can proceed in a controlled manner as in a nuclear reactor at a power plant or proceed uncontrollably as an explosion. If the chain reaction is taking place in controlled manner, it will result in a controlled power output, right? If the chain reaction is uncontrollable, it will proceed to an explosion. In a uranium-235 fission chain reaction, the fission of uranium nucleus produces high energy neutrons that go to split more nuclei. The energy released in this process can be used to produce electricity. This is the representation of this chain reaction. Uranium-235, bombardment of a neutron. Now you see the chain reaction, the daughter nuclei are krypton and barium. Further, it results in 3 neutrons, another U-235 nucleus, another one. Again, it will result in this manner. The process will proceed in this manner. If it is not controlled, it will result in explosion. Nuclear fusion. Fusion is a reaction through which 2 or more light nuclei collide into each other to form a heavy nucleus. This reaction takes place with elements that have a low atomic number, such as hydrogen. It is the opposite of nuclear fission reaction, in which heavy elements diffuse and form lighter elements. Both the fission as well as fusion produce a massive amount of energy. The important example of nuclear fusion in the nature is production of energy in the sun. It is known to us. Now let us see the representation of a nuclear power plant. The nuclear power plant is based upon the nuclear fission, right? So this is the schematic representation. What you can see over here is the reactor power vessel. This is the area where nuclear reaction takes place. The heat generated during the reaction is carried by some fluid to some area where steam generation takes place. The steam so generated is used to rotate the turbine. The shaft of the turbine is coupled with the shaft of the electrical generator, which is responsible for generation of electrical power, right? The steam output of the turbine, after rotating the turbine, the steam comes out. The steam is condensed. It gets converted into water. That water is again sent to the steam generator, where the generation of steam again takes place. For condensing the steam, for cooling down the steam and converting it back to the water, some coolant is required, right? So here you can see the flow of coolant in this vessel so as to condense the steam. This is said to be the primary loop. This is said to be the secondary loop. The primary loop incorporates the reactor itself and the system which is used for transfer of the energy produced inside the reactor for generation of the steam. This is the secondary loop. Secondary loop is actually the loop of the steam and converting steam back to water, sending it again to the steam generator. You can see this portion, they are representing the fuel rods inside the reactor. They contain the nuclear fuel. Fuel rods actually contain the nuclear fuel. It is, for our reactors, it is uranium-235. They are surrounded by the moderator, and as moderator we may use water or graphite. What is the purpose of the moderator? To slow down the neutrons released after the fission process. See the control rods. They control the rate of reaction by moving them in and out of the reactor. If all the control rods are kept inside the reactor, then it will cause shutting down of the reactor. The manner in which they are taken out, the amount by which the fuel control rods are taken out of the reactor are actually an indicative of the rate of reaction taking place inside the reactor. The control rods are made up of boron or cadmium, and that can absorb the neutrons. So control rods actually work upon the process of neutron capture. Here you can see a pump. The steam derives a turbine which turns the generator. The electricity so produced is connected to the grid. A pump is required over here in this circuit, in this primary loop, for flow of the coolant. Another pump is required in the secondary loop for flow of the water. Two separate water systems are used to avoid the radioactive substances to reach in the turbine. This is one water system and this is another water system. The first water system, the first system or the first water loop is actually for transferring the heat generated here to the steam generator for generation of the steam. And the second loop is actually the steam and water loop. So steam, after passing through the turbine, is condensed, converted to water and sent back to the steam generator for generation of steam. The energy released in fission heats up the water around the reactor, and the water in the secondary loop is boiled to the steam, which I have told you on previous slide. So this is all about this lecture. A brief of nuclear reactor and nuclear energy conversion system is discussed in this particular lecture. In next lecture, we will discuss in detail the type of nuclear reactors and the type of nuclear and based upon those the type of nuclear power plants. Thank you.